Hello and welcome to the 12th session of the Introductory Biostatistics Distance Learning course. Today's lecture is going to be about nonparametric tests. Before we get started, just a word about where we've been. So previously we'd thought about hypothesis testing and studied one sample and two sample t-tests. Those were for continuous outcomes with in the case of a two-sample t-test with a binary predictor or covariate, and then we moved on from there to the natural progression to analysis of variance or ANOVA, which again requires a continuous outcome, but in this case has a categorical predictor for more than two groups. And then we also talked about confidence intervals for these different accompanying tests. So today we're going to talk about nonparametric tests, such as the Wilcoxon-Signed rank test and so on. And we're going to think about when nonparametric tests might be appropriate, how to use ranks for nonparametric tests, and things like that. So let's motivate this. So remember we had talked about t-test and ANOVA, and we had both said that both of them require this assumption about underlying normality of the data. The data need to look normal. So when you plot the data, hopefully it has a normal shape like this, right? So again, this is a continuous outcome, and then you plot it with your histogram or whatever plotting technique you prefer, and hopefully you come up with something like this that looks normal. And usually things do look like this as you start to get large sample sizes. But what if we are unwilling to make this assumption about the underlying normality of the data and we have a small sample size? Sometimes we'll have 15 or 10 or even fewer subjects to work with. And with such a small sample size, we might be unwilling to assume normality. So one potential remedy for this problem is to use a nonparametric test, okay? And so as the name implies, these are statistical tests that make very few assumptions about the underlying distribution of the data. So to help you understand the word nonparametric, when you assume normality, that's called a parametric assumption. You're assuming these parameters, the mean and the standard deviation, which govern the normal distribution, are appropriate for your data. So in a nonparametric test, you're not assuming, you're not making these parametric assumptions, okay? And so once we decide that we're going to go forward with a nonparametric test, the steps of hypothesis testing are the same, but what's going to change is the null hypothesis that we're testing and also the calculation of the p-value. Okay, so let's try to make this a little bit more concrete with the use of an example. So there's this thing called diffusion tensor imaging, which is a new approach for investigating damage to the brain. Okay, so it's called diffusion tensor imaging. Again, don't worry about this particular, this is just an example. You don't have to worry about the specifics of it. And so we know that there's increased damage has been observed along many pathways in adult patients with multiple sclerosis or MS. And we wonder, is there a similar damage in pediatric MS? Okay, and so the design of this study to investigate this question, this is a kind of cool design that we haven't talked about so far, I believe. So we're going to measure ADC, this continuous outcome of interest. Again, always think about the types of variables you're working with. This is a continuous outcome in pediatric MS patients. And then we're going to find age, gender, and scanner matched healthy controls. Okay? So before we had just talked about taking random samples of certain populations. This study, however, we're talking about doing some matching. So we find cases, these are the children with MS, and then we find age, gender, and scanner matched healthy controls. Okay, then we compare the difference between the MS patients and the healthy controls. Okay, so a bit of a cool study design where you use this matching, the matching of age, gender, and scanner to get controls that are similar in all regards except for their MS. Okay, so you can see how matching would be helpful, because if we just took random samples, we might say, oh, our healthy controls had different ages or had a different distribution of gender and so on. But when we do this matching, it takes care of those factors that we might that we think could be important. Okay. So so to proceed with this particular example, what we would do is look here. So we look at the corpus callosum. Sorry if I'm pronouncing that incorrectly. You physicians probably certainly know this stuff better than I do. And so, okay, so now we have matched pairs, remember? That's why this says pair. So this is actually, a pair consists of one patient, those are the people with MS, a healthy control, and then we have this measure on each of them, and then the difference. Okay, so the patient had 1.11, the control had 0.91, and the difference between these is 0.2. Okay, so does it appear that there's a difference between patients and controls? Well, as I look down, and again, you'll notice I only have 10 patients to work with, so a small sample size, and so you can see why we're using this as an example for nonparametric testing, because with such a small sample size, we might be unwilling to assume normality. But as I scan down here and I look at the differences, it turns out all of these differences are positive, right? There's no negative differences here, and that means that all the patients had higher values across the board than the controls did. Okay, so it really does look like there's a difference between patients and controls. Namely, it appears that the patients have higher values consistently. So let's look at a histogram, which will be helpful to us to get a sense for our assumptions. Here's the histogram, and again, remember, we only have 10 patients. This is the distribution of the differences. So the differences in ADC, and it certainly doesn't look normal. You know, if we were to draw a normal distribution there, it doesn't look that good for normality. So we might think about not using the t-test or other tests that we've learned about that assume normality. Okay? Okay? So were we to conduct a one sample t-test of the difference or a paired t-test, we would write our null hypothesis, if we were going to proceed in that way, would be that the mean difference is equal to 0. Okay? So in this case, as we just saw from that histogram, we don't want to assume normality, so the mean may not be a good measure of central tendency. Okay, remember in the very first class, we talked about situations where we have skewed or non-symmetric distributions, and in those cases, the median is sometimes a better measure of central tendency. Okay, so Let's start thinking about our first nonparametric test. The simplest of all the nonparametric tests is called the sign test. Okay? And so what are the null and alternative hypotheses for the sign test? Well, the null, you guessed it, involves the median. No longer the mean. This is the first hypothesis test that we're doing that involves the median. So it says the median of the differences is equal to 0. And the alternative hypothesis is, again, that the median of the differences, if I can just say the median of the differences is not equal to 0. Okay? So, under the null hypothesis, note again that we're taking one number from a patient and then subtracting the corresponding measure for the matched control, the healthy control. So under the null hypothesis, that being the median of the differences is equal to 0, we would expect the same number of positive and negative signs, right? So another way of writing this would be that the null is the probability of a positive sign, and when I say positive sign, I mean for the difference. So I take a difference. The probability that that difference has a positive sign, remember a difference can be positive or negative, so the probability that that difference is positive should be half, right? Should get, when I take these differences, if there's really no relationship between these things, then half of my differences should be positive and half should be negative. Okay? But if most or all of the differences are positive, then that would give me some evidence against the null hypothesis. Okay? So let's continue with this example here. Okay, so we have our 10 pairs, the patient, the control, the difference, and then the corresponding sign of the difference. You see, these are all pluses because all the differences here are all positive, which is why these are all pluses. Okay, so if there was truly no effect of the therapy, we would assume that there would be an equal number of positive and negative signs. But here we have only positive signs. Okay, so this would suggest that there is an effect. There is something going on here. The patients all appear to have higher values than the controls. Okay? So, can we calculate a p-value for this sort of situation where 10 out of 10 were positive signs? All of these turned out to be positives. Can we calculate a p-value for this situation? Okay? And then it's always important and helpful to remember the definition of a p-value. Okay? The p-value, again, is the probability of the observed value or something more extreme under the null hypothesis. Oops. When we say under the null hypothesis, we mean that's the same thing as saying assuming that the null hypothesis is true. Okay? Okay, so for the sign test, this is the probability of the observed number of positive signs or more. And don't worry if you don't remember this, but we can calculate this p-value using the binomial distribution that we learned about way back when. Remember, the binomial distribution applies to cases where there are two outcomes. Here we're looking at differences and the sign of those differences. So that the sign of the difference is either positive or negative. And so since there are only two possible outcomes, the binomial distribution can be used here to calculate the p-value. So we want the probability of all 10 of our differences being positives. Okay? So remember, we had all 10 of our differences were positives. What's the probability of this? We're using the binomial distribution. So this is 10, choose 10, because all 10 of these were positive signs. And then 0.5, that's the assumed probability of a positive sign to the 10th. And then 0.5, the assumed probability of a negative sign to the 0, because none of our differences were actually negative. Okay? And if we use a computer, it would tell us that this is 0.00098. This is a one-sided p-value. Okay? One-sided p-value. Okay? And so since it's so small, we would reject the null hypothesis and conclude that there is an effect of the therapy. Okay? So that's our one-sided p-value. So remember this issue of one-sided versus two-sided tests. Always good to have those clear in your mind. So we had a one-sided p-value that we just calculated. If we wanted to make that p-value two-sided, what would we do? Well, we just know that a two-sided p-value is equal to 2 times, that's a multiplication sign, 2 times the one-sided p-value. Okay? So before our p-value was, our one-sided was something like 0.0010, was very close to that. So the two-sided p-value would be 2 times 0.0010 or 0.0020. That would be our two-sided p-value. Okay, so let's go through our 7 steps of hypothesis testing to complete this particular example. So in step 1, we want to write the null hypothesis. So the null hypothesis here is that the median difference is equal to 0. And the alternative would be that the median difference is not equal to 0. Between those two things, we've covered all possibilities. Then we want to talk about the type of data that we're working with. Well, we have a one-sample situation. This is kind of confusing. This is a paired situation, right? Because we have a diseased patient and then a corresponding matched healthy control. So you might be tempted to call it a 2-sample situation, but it's actually a paired. You can either think of it as a 1-sample situation or a paired situation. But importantly, we have a continuous outcome. Okay? We have a continuous outcome here. And then, once we know our null and alternative and the type of data that we're working with, we can determine the type of test we're going to use. Here we're going to use the sign test because we only have 10 patients. We looked at our histogram. It didn't look very normal, so we weren't comfortable making the normality assumption that a t-test would require. So instead, we're going to use a nonparametric test, the sign test. Our test statistic, remember, for the sign test is the sign of the differences, and in this particular case we had all 10 were positives, okay? We calculated our two-sided p-value using the binomial distribution, and that was equal to 0.0020. Okay? Those are my first 5 steps of hypothesis testing. In step 6, I say that since the p-value is less than 0.05, we reject the null hypothesis. Okay, we reject the null hypothesis here. And finally, in step 7, we need to reach a conclusion, and we conclude that there is a significant difference between the ADC, that's our outcome measure, in controls versus in patients. Okay, so not only is there a significant difference, that's probably not enough to say, but it appears that the ADC in controls is significantly higher, right? We saw that the controls had higher values than the patients, okay? Okay, good. So you can see how the 7 steps of hypothesis testing didn't change, but what did change is our null hypothesis changed. We were no longer looking at the mean. Instead, we were looking at the median because we had a nonparametric test, and the calculation of the p-value and so on also changed. But the steps of hypothesis testing did not. So what would the corresponding stata output for this test look like? Here is this. So the command is sign test. And then we have this variable. And so you can see it assesses the number of positive signs and the number of negative signs. There can also be 0, right, if the 2 numbers are exactly equal. We observed 10 positives, no negatives, and no ties. But we would have expected that 5 would have been positive and 5 would have been negative. And so now stata gives us the one-sided p-value here and also the two-sided p-value here. Okay, so a neat and easy way to conduct the sign test in stata. Okay. Okay. So now let's move on to another example. Let me just bring up the. Here we go. So we're looking at the cerebral peduncle here. And again, we're interested in the difference between 2 measurements, the patient and the control. Okay, so a very similar example to the one we were just working with. Okay, so here's the patient, here's the control, and here's the difference. And so now this time you'll notice there actually are some negative differences. Here's a negative difference, and here's a negative difference. So 2 out of our 10 have negative signs this time, and 8 out of 10 have positive signs. So does it appear that there is a difference? Okay, so now we have to decide, do we want to use a paired t-test, or do we want to use the sign test again? And so in order to make that determination, we're going to look at a histogram of our differences. Okay, so let me look at a histogram of the differences in this particular example. And that looks something like this. Again, a normal distribution doesn't really look like it fits this sort of this particular example, and we have a very small sample size, again, another 10. So we could use the sign test, which we just learned about, but there's another more powerful test. Note that when I say a test is more powerful, what that means is it's more likely to detect a difference, okay? So there's another more powerful test, one that's more likely to detect a difference than the sign test, and that's called the Wilcoxon signed rank test. Okay? So the Wilcoxon signed rank test. Okay, so the Wilcoxon signed rank test, just as the name implies, uses not only the sign of differences, which we were using before, but also their rank. Okay, so the null and alternative hypotheses are the same as they were for the sign test, namely that the median difference is equal to 0 in the null, and in the alternative that the median difference is not equal to 0. Okay? So let's take a look at some example data and how this sort of thing for the Wilcoxon signed rank test proceeds. Okay. Actually, let me just clear this out and start with a fresh page so we can see things better. Okay, that's better. So we have our 10 pairs, we have the patient, we have the control, we have the difference, and now we have this other thing called the rank, okay? And you'll see that things are ranked not by their actual values, but instead by their absolute value. What do I mean by that? Well, this negative 0.015 is the smallest value. That's why it gets this number 1 rank. Then in absolute value, 0.042 is the next smallest number, so that gets this number 2 rank. Then again, in absolute value, 0.098 is the third largest, so it gets the 3rd rank. And you can see this negative 0.102 in absolute value again is the 4th largest, so that's why that gets the number 4 rank. So if we were looking just at the actual values, this 0.102 is the smallest of all the numbers. It's the most negative, it's the smallest of all the numbers. But again, when we do the rank, we're looking at the absolute value. So that's why this is the number 4 rank as opposed to the number 1 rank. Okay? Because it's in terms of absolute values. Okay? All right. So now that we have that, our next step is to try to calculate a p-value for the Wilcoxon signed rank test. And the best or most accurate way to do this would be to use an exact test using kind of the distributions that these things come from. And this can be done with modern computing that we have today. You know, all those permutations and things like that, a computer can easily calculate to get to the p-value. But this wasn't really possible before many years ago. So people use these approximate Wilcoxon tests. Okay, so just kind of for purposes of illustrating what we might have done, we're going to talk about how we could calculate a p-value using the approximate Wilcoxon test. Okay. So how does that proceed? Well, we have this statistic here, which we call a z, right? So the approximate Wilcoxon test, I should write that here, the approximate Wilcoxon test, okay, uses the normal approximation in this way, okay? So first we have to define our numbers. So this t here is the sum of the positive ranks. Okay, remember on the previous slide we had given ranks to all the numbers there, but some of them were positive and some of them were negative. So this t here, this random variable called t, is the sum of the positive ranks. And then mu sub t is the expected sum of the ranks. Sum of the positive ranks. Under the null hypothesis. Okay, and then you guessed it, the sigma sub t is the standard deviation of the sum of the positive ranks under the null hypothesis. Okay? So we use all those things to define this new statistic called z. Remember, we use this z notation when we were talking about standard normals. So we would take a random variable, subtract off its mean, divide by its standard deviation to standardize it to the standard normal. Okay? Okay. So let's talk a little bit more about mu sub t and sigma sub t. Okay, so under the null, we would expect the sum of the positive ranks to equal the sum of the negative ranks, right? And that would be half of the total sum of ranks, okay? So under the null, we would expect the sum of positive ranks to equal the sum of the negative ranks. And we would expect both of those to be equal to half of the total sum of ranks. Okay? So, this is kind of a cool trick. So if you want to see what the sum of ranks are, here's a good way to think about it. So suppose I'm trying to add up all the numbers from 1 plus 2 plus 3 plus 4, so on, all the way up to plus 96 plus 97 plus 98 plus 99 plus 100. Trying to add up all the numbers from 1 to 100, right? Well, I can match these certain numbers, right? I can say, if I add up the 1 with the 99, I get 100. If I add up 2 with the 98, I get 100. 3 with 97, I get 100. 4 with 96, I get 100, and so on. And I can just continue that process all the way up to the number. I can just continue that process all the way up to adding 49 plus 51 to give me 100, right? So that would give me 4,900, right? And then I know that I have this 100 left over here. So that gives me, plus 100, I have 5,000. And then right in the middle, there's a 50 left over. There's 50. So then I have to add, this 50, and that gives me 5,050 as the total for adding up 1 to 100, okay? And so a simple formula for adding up 1 plus 2 plus ... all the way up to n is n times n plus 1 divided by 2. Okay? And so if we do that in our particular example of adding up all the way to 100, then that is 100 times 101 divided by 2. So let me check that. That's 10100 divided by 2, which is 5050, okay, which is what we got before. Okay, so if you're ever trying to add up the numbers from 1 all the way up to n, the formula is n times n plus 1 divided by 2. Okay, so why is this relevant? We're trying to add up the sum of positive ranks, right? And so we expect that to be the same as the sum of negative ranks. And so we expect mu sub t to be n times n plus 1 divided by 2. That's the formula we have. And then we expect half of them to be positive and half to be negative. So that's the same as saying n times n plus 1 divided by 4. Okay. And we won't go through a similar derivation for the standard deviation. I'll just present the formula instead, and that is sigma sub t is, actually, let me just pull the corresponding, okay, whoops. So we had this as our statistic, and then we said that here is the formula for mu sub t. Remember we said that that 1 plus 2 plus ... n is equal to n times n plus 1 divided by 2. And the reason that mu sub t is divided by 4 is because we expect half of the ranks to be positive and half of them to be negative. And mu sub t is the sum of the positive ranks. Okay? And then finally, the formula for the variance given here. Okay? All right. So for our results, so let's go back, let's go back to this particular example that we're working with, which was here. Okay, and remember we said that mu sub t is the sum of the positive ranks. Okay, so where are the positive ranks in this example? So this is a negative, so this is out. This is a negative, so this is out. The rest of them are positive. So it's 2 plus 5 is 7, plus 7 is 14, plus 8 is 22, plus 6 is 28, plus 9 is 37, plus 10 is 47, plus 3 is 50. Okay, so mu sub t in this example is equal to 50. See what I did there? I took only the positive differences. So here's a positive difference. These are all positive differences. The only two that are out are these two. And then I added up the corresponding ranks for all those positives. And I got to mu sub t being equal to 50. Okay? So the sum of positive ranks, whoops, sorry about that. This is not mu sub t, this is t. Sorry about that. So t is equal to 50 in this case. Okay? So t equals 50. Now, mu sub t is the expected value of the sum of the ranks. What is that equal to? Remember that mu sub t, we said, is equal to n times n plus 1 divided by 4. N here is 10, so 10 times 11 divided by 4. That's 110 divided by 4, which is 27.5. Okay? So let me clear that out and say t is equal to 50. And then mu sub t is 27.5. The standard deviation in this particular example would be 9.81. And so now we have all the things we need to construct our approximate test statistic. What would that look like? That would be this. So we take t, which we said is 50, subtract off mu sub t, the 27.5, divide by sigma sub t, 9.81, and then we get 2.29 as our approximate statistic. Okay, that's a z statistic, the standard normal, and so we can get a p-value by looking at corresponding normal tables. So just for purposes of completeness, let's go through our 7 steps of hypothesis testing. Step 1, state the null and alternative. The null hypothesis is that the median difference is equal to 0. The alternative is that the median difference is not equal to 0. We're in a one sample, but it's paired. A one sample paired situation with a continuous outcome. Okay? Again, by paired we mean that there's a healthy control and a diseased subject that are matched. So continuous outcome variable. And we've decided to use the Wilcoxon because normality does not look justified. We looked at the histogram. It didn't look normal. We only have 10 patients, or 10 matched pairs, I should say. So we've decided to use the Wilcoxon signed rank test. Okay, our test statistic, which we calculated on the previous slide, was z equal 2.29. We can get a p-value for that by looking at the standard normal tables. And it turns out the p-value in this case is 0.022. Since this is 0.022 is less than 0.05, we reject the null. Okay? We reject the null because our p-value is less than 0.05. And then finally, in the last step, we conclude that the difference is greater than 0 In other words, pediatric MS patients have a higher outcome than controls. Okay? And that's our final step of our hypothesis testing. Okay? And so that, if we just go back to our data set, that makes sense, right? So here are the patients, here are the controls. So you can see the patients almost across the board have higher values than the controls. Okay, so our conclusion makes sense. It definitely does appear that pediatric MS patients have a higher outcome than controls on average. Okay. All right, what does this look like in Stata? Let me pull up some output. Okay, so Wilcoxon's signed rank test is what we're doing. The command is sign rank, and it'll tell you all the things that so there, There were 8 positive signs and 2 negative signs in this particular example. The sum of the ranks for the positives was 50. That was that t statistic that we calculated by hand. Under the null hypothesis, we would expect half of the differences to be positive and half negative. So half of 55 is 27.5, which is why that is there. And then the corresponding p-value is down here, 0.0218. Okay? So that's less than 0.05. We would reject, and we conclude that the patients, the MS patients, have higher values of the outcome than controls. Okay? Good. So what do we do if there are ties? That is to say, if we have a patient and a control with the exact same value, okay? Or rather, if we have multiple observations that have the same value. If we have multiple observations with the same value, we just give the mean rank to each observation. The mean rank is assigned to each observation. Okay, the variance is adjusted to account for the ties, but all of this is done in Stata, so you don't have to worry about it too much. Okay, so just in terms of comments to wrap up this section, when we want to complete a one-sample hypothesis test and the underlying data are not normal, we can pursue nonparametric tests. We have the Wilcoxon signed rank and then also the sign test, but we usually prefer the Wilcoxon signed rank test because it's more powerful. It uses more of the data, not just the sign of the differences, but also the rank of the differences, and it's therefore more powerful. Okay, but one thing to keep in mind is that the Wilcoxon sign rank test assumes symmetry and the sign test does not. Okay. All right. So that was for the paired setting, right? Remember the examples that we worked with where there was always a patient or a diseased person, and then we had a matched healthy control. What if instead, so that's a dependent case. What if instead we have independent samples and we want to go forward with a nonparametric test? We now do the Wilcoxon rank sum. Okay, so before we had the Wilcoxon signed rank, now we have the Wilcoxon rank sum for independent data. Okay, so let's think about an example. Okay, so the main outcome measure in multiple sclerosis is the Expanded Disability Status Scale. Okay, the EDSS, Expanded Disability Status Scale. Okay, the EDSS is a 0 to 10 with steps of, it's a 0 to 10 scale with steps of 0.5. Okay, so this is an ordered scale, or rather an ordinal scale, so it's ordered, but the magnitude between steps is uncertain. Okay, so I guess a lot of people believe that the steps of the scale are just a rank, not a measure of magnitude. And as a result, since it's an ordinal scale, a t-test is not appropriate, right? Because this is not a continuous outcome, it's an ordinal outcome. Okay? So when it comes to multiple sclerosis, most patients with MS develop the disease between ages 20 and 40, but a subset of patients develop MS at a younger age. And a question of research interest might be, what is different about the patients who develop pediatric multiple sclerosis versus those who develop it as adults? Okay? And so if we investigated patients at a similar disease duration, is there a significant difference in this measure called EDSS, the Expanded Disability Status Scale? Okay? So since we have two independent samples, the pediatric versus the adult, we could use a two-sample t-test. But unfortunately, we know that we have ordinal data, so the t-test is not appropriate. Okay? So let's look at some data to make this a little bit more clear. Okay? So here's some data output with the tabulate command. It's just group by EDSS, the outcome. And so this just tells you the number falling in each of these categories. Okay? So we want to see, it's not clear from these labels of 1 and 2 which is pediatric and which is adult, but we want to see whether they differ with respect to their EDSS outcomes. Okay, so we're going to proceed with the Wilcoxon rank sum test. Okay, and so the reason we're doing this is because we have two independent samples. The t-test is not appropriate. It's not appropriate because we have an ordinal outcome. So therefore, we're going to proceed with the non-parametric test for two independent samples called the Wilcoxon rank sum test. Okay. So the Wilcoxon rank sum the null hypothesis is that the distribution, so the way we write that is this capital letter F, the distribution, the distribution of the outcome for adults is the same as the distribution in kids, pediatric. Okay? And the alternative hypothesis is that the distributions are not equal. But if we assume that the difference between the distributions is just a shift in their location, then we could just write it in the way that we had before, namely that the median in adults is equal to the median in kids, and then the alternative would be that the medians are not equal. Okay? All right. So let's make this more concrete, following through with our example. Okay, so here's, you'll notice now that we no longer have pairs, but instead just patients. Looks like we have 7 patients. Here's the EDSS. This column gives their outcome. This column tells us whether it's an adult or a pediatric patient. And then the final number gives us the rank, okay? So you can see the smallest number here is 0 for EDSS, so that gets the rank of 1, okay? Then the next smallest number, it looks like, is 1, but that appears twice. So here we have a tie, okay? So one of these, so this is, these two numbers should get the second and third ranks, right? We've already given away the first rank. So the second and third rank need to go to these. So we just take their mean. and give each of these 2.5. The mean of 2 and 3 is 2.5, so each of those gets a rank of 2.5. Similarly, the next biggest number also appears twice, 1.5. And so the ranks that would need to go to these two observations are 4 and 5. So we just take the mean and get 4.5 and assign the rank of 4.5 to each of those. Okay, then the next largest number is 2, that's the 6th rank, and finally the largest number is 3, that gets the rank of 7. Okay, just like we did before, we're going to proceed with an approximate Wilcoxon test. Okay, and so if the sample size is large enough, an approximate Wilcoxon test based on the normal approximation can be used. Usually a good rule of thumb for this sample size is if you have 20 or more patients. Here we have 7, so that might not even hold, but just for purposes of illustration, we'll proceed with that. So that's the form of our test statistic here, just like we saw before. Now we have these new variables to define. W is the sum of the ranks in the smaller group. Okay, so what do we mean by that? Well, we're going to add up the ranks for the adults, we're going to add up the ranks for the children, and whichever one of those sum of ranks is smaller, we'll call that W. Okay, mu sub W is the expected sum of ranks in the smaller group under the null. Okay, and similarly, sigma sub W is the standard deviation of the sum of ranks in the smaller group under the null. Okay? All right. Okay, so let's talk a little bit more about what we mean by mu sub W and sigma sub W. Okay, so under the null of no difference between the groups, the expected sum of ranks in the smaller group is given by the following formula. There, and the standard deviation is here. Okay, I'm not going to get into the derivation of these like we did for the Wilcoxon signed rank test, but these are the formulas, and so they'll be useful for us going forward. Okay, so from our results, so what does it look like for our results? So it turns out there were actually many more than 7 patients, but those were, the first 7 were just shown for illustrative purposes. So the sum of the ranks in the smaller group, which is called W, turns out in this example to be 1654. Okay, and the mu sub W, using the formulas that we just had on the previous slide, is 1430. Sigma sub W is 159.7. And so as a result, our Z statistic, using, here's W, minus mu sub w, 1430, and then here's our w here, 1654, divided by mu sub w, 159.7, gives us this 1.4 for our standard normal, the z statistic. Okay? And again, ties and all those sorts of things are going to be handled by Stata, so we don't have to worry about doing this by hand. Okay? But let's write out the 7 steps of our hypothesis testing. So step 1, the null hypothesis, is that the distribution, remember we write that with the big capital letter F, in pediatric patients, whoops, this is supposed to be an X, is equal to the distribution in adults. The type of data that we're working with is an ordinal outcome with a dichotomous predictor. So remember, the ordinal outcome is this measure, the EDSS measure that goes from 0 to 10. The dichotomous predictor is, are you an adult or a child? Is the patient an adult or child? We have independent samples, so and we want a nonparametric test since we have the ordinal outcome. We can't use a t-test because we have an ordinal outcome. And so therefore, the test that we're pursuing is called the Wilcoxon rank sum test. And then we use Stata to give us test statistic. So the test statistic in this case is z equals 1.45. The corresponding p-value from Stata, again, the computer calculates all this for us, so we don't have to worry too much about it, is 0.15. But this is where the human comes back into it because we need to interpret these results that the software gives us. So then we say that since 0.15 is greater than 0.05, we fail to reject the null hypothesis. Remember, we always say that we fail to reject. We don't accept the null because it just might be the case that we don't have enough samples or enough evidence and so on. So we just fail to reject the null. And so we conclude that based on our sample, sometimes it's good to say based on our sample to make it clear that when we fail to reject, again, we might have failed to reject just because we didn't collect a large enough sample size or some similar reason. So based on our sample, there is no significant difference in mean EDSS in adult, sorry, I'm running out of space, in adult and pediatric MS patients. Okay, so just a few things to remember. So that based on our sample, we failed to reject, so that's kind of good to put. And then there's no significant difference in mean EDSS, okay? All right. Or sorry, shouldn't be using the, I got myself confused. Remember, we're doing a nonparametric test, so we're not doing a test of the means anymore. My apologies for that. Good thing I caught that. So there's no difference in EDSS. We want to get rid of this mean word. We use that mean word when we're using t-tests and so on, but we're in the nonparametric setting. So we don't want to use that word mean. Okay. So what would this look like in terms of stata output? Be here. So the stata command is rank sum. EDSS is our outcome by group that separates adults and children. You'll notice that the Wilcoxon rank sum test, just to confuse you even further, has another name called the Mann-Whitney test also. So those are the same thing. The Wilcoxon rank sum test is the same as the Mann-Whitney test. And again, it looks like we had very unequal sample sizes in the two groups. 22 in one group, 107 in another group. So that's why the expected, even the expected sum of ranks is different when you have such different sample sizes. But then here's the observed sum of ranks, and then here's the corresponding p-value here, 0.1463. Okay? So we fail to reject in this case. Okay, so just some general comments. The Wilcoxon rank sum test is common in some settings, but it's important to remember that it assumes the same shapes of the distributions. Remember, our null hypothesis was that the distribution in the first group was equal to the distribution in the second group. It assumes the same shape. So there's not a large loss of power in using a Wilcoxon rank sum test compared to a t-test, even if the normality assumption holds. But remember that if normality does not hold, or if we have ordinal data like we did in the example, the Wilcoxon test is preferred. Okay, so let's look back at this this development, this table of analyses that we've been developing now through the course. Again, we always think about the type of outcome variable we have, the type of explanatory variable we have, the type of outcome, type of explanatory, and that tells us the type of analysis we need to conduct. And so today we talked about an ordinal outcome for the first time with a dichotomous explanatory, adults versus pediatric, and we used a Wilcoxon test. Okay? All right. So what are some, let's talk a little bit about, here's a parametric test. And then what's its non-parametric equivalent? Okay, so we had the paired t-test. Remember, the paired t-test is for matched controls and things like that. So when we were in the paired situation, we had the paired t-test, and we used the non-parametric equivalent was the Wilcoxon signed rank test. Okay. Then when we had a two-sample t-test, when we had independent samples, and we had two different groups, so it was a two-sample t-test, the non-parametric equivalent was the Wilcoxon rank sum test. And then finally, if we were going to do ANOVA, which is a parametric test, there's this equivalent called the Kruskal-Wallis test. Okay? And that's another rank, the Kruskal-Wallis is another rank-based test for situations when you have two or more independent samples. Okay? All right, so I'll stop there with nonparametric tests, and I will see you in the next session where we'll talk a little bit about bootstrap and permutation tests. Okay, see you then.